Unit 9, Day 2 video notes, working with radicals. Okay, so now finding the square root when we have not just a number, but variables and exponents inside. Let's start off first dealing with the number. And so we'll go ahead and do a factor tree. And we've got 2 times 24. 12. Circle primes. Okay, so now let's write out what we've got here. We have the square root of, and I'll finish that in a minute. And we've got 2 times 2 times 2, got 4 2's, times 3, and then we have x times x times x times x, and then times y times y times y. And all of that is in my square root. So let's see what we have now. We have a set of 2 2's here, so the square root of that is 2. We have another set of 2's, its square root is 2. There's only one 3, so it's going to stay inside of the radical. We have a set of x's here, so its square root is x. Another set of x's, its square root is x. A set of y's, so its square root is y. And then we have a y left inside of the radical. So let's take a look at it. Outside of the radical, we have 2 times 2, which is 4. X times x is x squared. And then y times the square root of, and let's see what's left inside, we have a 3 and a y. So the square root of 3y. Pythagorean theorem. The Pythagorean theorem tells us that if we have a right triangle, then the square of one leg plus the square of the other leg will equal the square of the hypotenuse. So let's see here. A leg is a side that's adjacent to the right angle. So both of these are legs. And the hypotenuse is the longest side, and it's opposite the right angle. It's this side here. So the hypotenuse, like I say, is always the longest side, and it's also always opposite the right angle. The other two sides are both legs. So now they gave us the length of 2 of the sides. We need to find the third one. In this case, the one we're finding is a leg. So what do we have here? We have, and I'm just going to replace this question mark with a variable x. We have x squared plus 15 squared equals 17 squared. So now we need to go ahead and solve this. First off, we have x squared plus 15 squared is, let's see here, let's double check what it is. So we've got 15 times 15, and that will give me Okay. 2, 7, and then, so what do I get here? 225. And 17 squared actually is 289. I happen to always remember this one because I used to have a car with that size engine in it. A 289 is a Ford engine. I had a 66 Fairlane with a 289 in it. Okay, so of course now we need to subtract 225 from both sides. And when I do this, let me go ahead and erase this multiplication problem that I did earlier so that it doesn't get in our way and confuse us as we're doing this subtraction. Okay, so 9 minus 5 is 4. 8 minus 2 is 6. 2 minus 2 is 0. So I now have x squared equals 64. To solve this, I now need to take the square root of both sides. I don't need to worry about plus or minus because I'm not looking for a negative number, only a positive one. And x now equals 8. So the length of that missing side is 8. Oh, I should mention one more thing with the Pythagorean theorem, and that is you can use this to determine, if you're given the lengths of sides, you can use this to determine if the triangle is a right triangle or not, because the squares of the two legs, when you add those together, should equal the square of the hypotenuse. If it does, it's a right triangle. If it does not, it is not a right triangle. Okay, now we have radicals with fractions in them and we're multiplying. I picked a harder example because it'll give us the opportunity to see a few things at the same time. So the first thing is that this is the same thing as putting the whole thing inside of the same radical. So we can now do the multiplying fractions the same way that we've always done it in the past, and ignore the radical until we get done with that, and we need to start doing any simplifying of the radical, plus one other thing called rationalizing the denominator that we'll get to in a minute. So I'm going to go ahead and do factor trees for the top and the bottom. I am going to go through the radical. Don't let that confuse you. Eleven is prime. Extend this page so I don't have to kneel down. 4, 2 times circle my primes. Okay. And good, I can see the whole thing now. And I can take care of canceling. Well, I've got an 11 and an 11, a 2 and a 2, a 2 and a 2, a 2 and a 2, a 2 and a 2. Okay, so everything's canceled on the top, and everything but the 2 has canceled on the bottom. So I am left with the square root of 1 over 2. I'm not done yet, however. And I need to move this down so that I can work with it better, so I'm going to rewrite it down here. The square root, let me undo that. The square root of 1 over 2. Okay, and the issue is that, well, first, before I get to that issue, we can break this apart into the square root of 1 over the square root of 2. Notice that with multiplication and division, I can treat them as separate radicals, or I can put them all under the same radical, and it works either way. They're the same thing. Now this is the same thing as 1 over the square root of 2, because the square root of 1 is 1. 1 times 1 is 1. 1 squared is 1. Now, I can't have a radical on the bottom of a fraction, so I need to do what's called rationalizing the denominator. To get rid of this square root of 2 on the bottom, I'm going to multiply it by the square root of 2. And if I multiply the bottom of the fraction by the square root of 2, I also need to multiply the top of the fraction by the square root of 2. And when I do that, the top of the fraction, 1 times the square root of 2, is the square root of 2. And the bottom of the fraction, the square root of 2 times the square root of 2 is 2, which is the reason why I multiplied it by itself, is to get rid of the radical. Okay, let's try rationalizing the denominator one more time. Let's do another example here. So I can rewrite this as 6 times the square root of 7 over 35. I moved the 6 from the top of the fraction to out in front of the fraction, which doesn't change anything. And then I took the square root of 7 over the square root of 35 and turned it into the square root of 7 over 35. Now I can go ahead and do some simplifying here. The 7 is prime and 35 is 5 times 7. I can cancel the 7's, and that leaves me with 6 times the square root of 1 over 5. Okay, so let me bring this down here. Whoops, that's not supposed to be there. Get rid of it. Let's see. Delete. Okay. So now let me rewrite it here. My pen back. 6 times the square root of 1 over 5. Okay. So now this is the same thing as 6 times the square root of 1 over the square root of 5. Well, the square root of 1 is just 1. So that's the same thing as 6 times 1, or 6 over the square root of 5. And I'm going to need to rationalize the denominator. To make things simpler, I'm going to rewrite this down here. Now we're going to multiply top and bottom of this fraction by the square root of 5. And when I do that, the top of the fraction becomes 6 times the square root of 5. And the bottom of the fraction, the square root of 5 times the square root of 5 is 5. I've now rationalized the denominator. There's no radical in the bottom of the fraction.